Thank you. This is a joint work with Ron Garcia and Eric Tenter. This work is concerned with making security typing more accessible by adapting some ideas of gradual typing. So first, we're going to explain what security typing is and its limitations. So in information flow control, there is a notion of confidentiality of values. So for instance, this variable pub, it can be public for us, so we tag it with some security label L, which represents some low security data. And we can have some other value priv, which for us is private, so we annotate it with some H security label, which represent high security data. And suppose that we have two other functions, into string and print, where print is a low security channel. And if we try to do print of into string of priv instead of print of into string of pub, then we're going to have a breach of confidentiality because we are exposing private information into a low security channel. So noninterference is the property that captures confidentiality in a general setting that can scale to arbitrary lattices, such as this one. Here is an example that we use during the presentation, where we have bottom, low, high, and top. And noninterference states that high security input do not affect the low security result, so high security information should not flow to low security context. So security typing enforces noninterference statically by indexing types with a security label. So for instance, this type here represents a private int, and this function here represents a public function that takes a public argument and returns a public boolean. So the same program that we have before, if we add the security annotations everywhere, then this program is going to be rejected statically because there is an invalid flow from high to low. And type soundness here states that well-typed programs satisfy noninterference. So security typing not only helps us detect explicit security flows, but also implicit security flows, because high security data can affect the control flow of a program. So here, for instance, we have two values, a public and a private value, and we have a conditional that depends on a binary operation between those two values. So the confidentiality level of the condition is computed by using the join in the security lattice. So this program should be rejected because we have a public output that would depend on a confidential input. And in the presence of mutable references, we can also have implicit security flows through the heaps, which are harder to detect. So security typing also induces free security theorems, and this is because noninterference is a modular reasoning principle, so it allows us to talk about open terms and functions. So if we rewrite the previous function in some function mixed, which takes as argument a public int and a private int and outputs a public int, then as a free security theorem, we know that the result cannot leak information about the second argument, because the second argument is private, the output is public, so otherwise it would be an implicit flow from high to low. So the problem with security typing is of course, it's a conservative approximation. Everything has to be security annotated. And sometimes it may be hard to find good annotations. And for some, it can be cumbersome to adapt if you don't have security typing. So we want to do an effort to overcome this limitation by combining security typing with gradual typing. So gradual typing supports the smooth transition between static type checking and dynamic type checking. Both has its advantages and disadvantages. Static type checking gives you early detection of error, but it's a conservative approximation. And dynamic type checking gives you flexibility, but at the cost of having extra runtime checks and errors. So gradual typing is about precision, where precision is a type relation. And imprecision is introduced mostly by the unknown type, which may represent any type whatsoever. So we say, for instance, int is more precise than unknown. The function from int to bool is more precise than the function from int to unknown, and that is more precise than the function from unknown to unknown, and that is more precise than unknown. Precision helps us derive consistency relations, such as consistency, which is the gradual counterpart of equality. So for instance, int is consistent with unknown, and unknown is consistent with int. And there are some desirable properties with gradual typing, such as type safety, which is guarded by runtime check when needed, the conservative extension of the static discipline, the embedding of the dynamic discipline, and the gradual guarantee that can be divided into the static gradual guarantee, which says that if a program type checks to a type, then a less precise type type checks to a less precise type. And similarly, the dynamic gradual guarantee says that any program that runs without error would continue to do so if it were given less precise types. So we have security typing and gradual typing and a lot of properties. And we want to see if we can combine these two concepts and satisfy all these properties. So most current approaches do not satisfy all these properties. So in this work, we present GSLRef, which is the resulting language of gradualizing SSLRef, which is a static security type higher the language with references, with support with first-class function, first-class references, and higher the store. And the only source of imprecision are security labels. So we do this by introducing the unknown security label. So this type here represents an int with an unknown security label. And this unknown security label is consistent with any other static label. So, and in this language, we aim to satisfy mainly noninterference and the free security theorems. So the previous function that the previous program that we had before in GSLRef can be written like this. And this is the sugared version, where wherever you don't have security annotation, you have an unknown security annotation instead. So if we want to enforce the policy that we defined previously, we just have to annotate only two security annotation, one in priv, we say priv is high, and one in the argument of print, meaning that print receives as argument a public string. So if we do this, this is going to type check, but it's going to give us a runtime error. So if we add just one extra type annotation in the argument of into string, then instead of having a runtime error, we're going to have a type error. So we go from having no errors to runtime errors to static errors by increasing the precision of annotations. So let's remember this function mix, which is rejected statically because there is an implicit flow from H to low. We can introduce imprecision on the second argument of mix. So we say now mix takes an int with a non-security label. This is going to type check now. And you don't have to insert any cast whatsoever. Everything is driven by types. So if you call mix, for instance, with two public values, you're going to get a public result, which is fine. Everything is public. But if you call mix with a private second argument, then you're going to have a runtime error. So we enforce termination insensitive and interference dynamically. So GSLRef also respect the free security theorem. So if we wrap this function mix into some smix function, and we can see that those two functions has different types, we know that they're going to give us different theorems because different signatures give us different theorems. So from the second signature, from smix, we know that the output should not leak information about the second argument. So if we call smix with any two arguments, it's going to give us a runtime error, even though the two arguments are public. Otherwise, we will be leaking information about the second argument. So GSLRef is derived using AGT, abstract gradual typing. And AGT takes as input a static language, which is type system and it's type safety proof. And you have to give the interpretation of gradual types. So you have to give meaning to gradual types on the static semantics and the meaning of evidence that is used on the dynamic semantics. And evidence justify at runtime why a consistent judgment holds. And if you follow the methodology, you get a gradual language with its own type system and its own dynamic semantics, where the dynamic semantics are based on proof-reduction and gradual typing derivation. And by construction, you get type safety, the gradual guarantee, the conservative extension of the static discipline, and the embedding of the dynamic discipline. So what about non-interference? So we first apply AGT using the same interpretation on for types and evidence. So we use gradual labels. And to use gradual labels, we have to define the meaning of gradual labels. Or this is via a concretization function from gradual types into set of types. So for instance, we say the meaning of int h is just a singleton type int h. And the meaning of int unknown is just the set of int indexed with every security label. And similarly, you have to define an abstraction function from set of types into gradual types. So for instance, the abstraction of the set of int h and int top is int unknown. Just an example. So at runtime, you have to compute sometimes the join between two types. So here we are computing, for instance, the join between a private int and an int with unknown security label. And this is going to give us int unknown, because this unknown is the result of abstracting the possibilities of the join, which is the set of h and top. The problem with this is that this int unknown can be used now as L. So we forget information about h, about private. So if we consider this function mix, where now the first argument is unknown, it has unknown security label, and if we call it with two different private second arguments, we're going to get two different public results. So this is breaking noninterference. So the direct application of AGT satisfies type safety, the static error guarantee, the dynamic error guarantee, the conservative extension, but we don't have noninterference. So what we actually did was a refined application of AGT, where on the dynamic semantic, we use label intervals in the evidence, where now types are indexed by some interval of static labels, where the interval represents all security labels between the boundaries. So for instance, the unknown type is now represented by the interval from bot to top. So for instance, now the abstraction of the set of int h and int top, it is now the int indexed with the interval from h to top. So previously we have this join. This join now at runtime is now the join between int from h to h, joined with int from bottom to top, and this is going to give us the abstraction of the set of h and top. This is going to give us the interval from h to top. So we actually remember information about h now. So if we call this function mix again, then we're going to have a runtime error. So using this refined application of AGT, we recover noninterference, but only for the pure fragment of the language. There are still implicit flow through the heaps, which are not prevented, because a program may leak information due to non-taken branches. So the dynamic detection of implicit flows through the heap is hard, because a leak through an executive branch, it may be not accessible to runtime monitors. And there are some techniques, many techniques. To name a few, we have dynamic techniques, such as the non-sensitive upgrade approach, which is very conservative, And we have some hybrid techniques, such as doing an effect analysis, which is still conservative, and it can also be very complex in a context with higher the language, like SSLref. And it can also be produce extra overhead for programmers. So in this work, we pick an approach similar to the non-sensitive upgrade. So we actually add an extra check in the assignment reduction rule, and with this, we get non-interference, we get the free security theorems, but we lose the dynamic error guarantee. And why is that? So consider this program here, where we have y, which is a private reference, and we are doing some assignment in a branch of a conditional that depends on a private value. So everything is private, so this is fine. This is reduced to unit. But if we introduce imprecision by changing now the security annotation of the reference y, so for instance, now y is an unknown reference, then we're going to see when we're doing the assignment if what's on the heap in that moment, which is something unknown, if the condition is always less secure than what's on the heap. So in this case, it's not always less secure, because a node, it can represent a low, for instance. So here we fail, we reduce to a runtime error. And this actually breaks the dynamic guarantee, because by introducing imprecision, now we're failing more. So there is a deep conflict between non-interference and the dynamic error guarantee due to mutable references. And as perspectives, well, we still want to see if we can reconcile non-interference and the dynamic error guarantee using other techniques, such as secure multi-execution or phasetic execution. But in this setting, we want to first give meaning to the dynamic error guarantee in this setting. And we could also try to do an effect analysis, which, as I previously said, it can be complex in a language which is high order. And we could also try to do it in a restricted language without first-class function or first-class references, which can be fully transparent for programmers. But we still don't know if we do that, it would allow us to recover the dynamic error guarantee. Other perspectives are integrating the Gradual label with a noun type, support for integrity, implement pay-as-you-go semantics, and so on. So to summarize, we apply the AGT methodology to a high-order security language with references, using different interpretation on the static and the dynamic semantics. We add an extra check on the assignment rule, and we get non-interference, but at the cost of the dynamic error guarantee. And you can see an online interpreter of the language in that URL. So thank you for your time.
We have some time for questions. I'll start with one from Slido. Someone asks, to what extent can the presence of runtime error be used to leak information?
So we don't have termination-sensitive non-interference, so it's termination-insensitive non-interference. So if you get a runtime error, you won't be able to leak information. So it's a weaker guarantee.
Is there a question in the room?
So this conflict between non-interference and the dynamic gradual guarantee, I guess part of my question is, maybe you sort of answered it, but how deep does that conflict go? And it sounds like maybe given other techniques for enforcing non-interference, maybe it's possible to have both, but could you comment on, just how deep do you think it goes?
Using other techniques to enforce non-interference?
Is there a hope to design a different system that gets both?
Yeah, well, if you don't have if you do an effect analysis and you can reason about the other branches, so you could have, I think that you could have the dynamic guarantee, but we still don't know. It's just work in progress. And it's hard because non-interference is a hyper property, and so it depends on two executions. So we have to, I don't know, you have to adapt other techniques that are not derived by AGT.
So any functional programmer would look at what you're doing and saying, well, of course you've got problems. You're using references. That was a silly idea. And we just had a session on effects, which lets you recapture things like state, but in a somewhat more disciplined way. So would adapting some of the ideas about effects from the previous session possibly help you recover?
Yes, that will be an interesting topic to follow, so do an effect analysis. So that's something that we want to try in the future. But it's get complicated in a higher language. So we want to make the use of gradual security types be like transparent for the programmer. So he doesn't have to reason about effects also. So it could be two things.
I have a question. Through the use of this unknown security level, you're trying to capture some kind of imprecision of security labels. Have you considered if you instead used label parametricity, would you be able to type the same kinds of programs without introducing this imprecision?
I'm not sure. I will have to see. I think that my impression is that no, because otherwise you would use this technique to gradual typing in a general setting. So I will have to look at it.
And a last question from Slido. It says, the security community is skeptical about IFC because of side channels. Can this help address some of those issues utilizing this typing discipline?
Side channels?
Yes.
Yeah, I'm not familiar with that, so we can talk about this offline.
All right, let's thank the speaker again.
Thank you.